Uh, Good morning. My name is Krishna. I'm with the Georgia Institute of Technology. This is YSense LLC is a startup based on Georgia Institute of Technology patents. What I'm going to talk about today is the nanotechnology-based sensors, which can detect environmental contaminants that have significant public health impact, especially for asthma and other respiratory diseases. And my collaborators are Dr. Elena Bekyarova, who is a renowned chemist in nanoscience, and Professor Patrizia Savi from Politecnico, Torino. So, a brief outline. I'll very briefly talk about nanotechnology-based sensors and why those sensors are important for public health. I'll touch upon the sensor design and measurement. Our sensor is a resonant sensor, but which is completely passive, meaning that there is no power connected to the device. And what we are trying to do is to measure the scattering from this passive sensor. So it can be, for example, the sensor can be mounted on a pole, and we can look at the scattering from the sensor remotely using a drone. This is just a proof of concept. It's a very initial stage of research. What I call this as backscattering resonance measurement. And I'll conclude shortly. So carbon nanomaterials, in this community, I don't need to give a detailed talk on this. There are several forms of carbon nanomaterials which are very useful in sensor applications: diamond, graphite, nanotubes, graphene, etc. But the most prominent materials that are consistently being used in sensors are the single-walled and multi-walled carbon nanotubes shown here, as well as graphene. Graphene is very promising, but still in the very early stage of research, and not many. There's no commercial sensor available which completely relies on graphene for this. So what is graphene? It is a single atom thick planar sheet of covalently bonded atoms densely packed in a lattice, like sorry, densely packed in a lattice like this. And carbon nanotube is basically a two-dimensional sheet rolled into a tube with very attractive surface chemistry that can be functionalized to detect a particular chemical. So nanotubes have this very attractive property, functionalization. So the way we are making these materials is we make flakes or nanotubes using the appropriate chemistry, and then we make a solvent of that. We sonicate it to get rid of agglomerates, and we deposit this solvent on a tiny area for the sensor using inkjet printing or spray coating or drop casting, etc. This is an example of a sensor from MIT, Professor Strong's group. Basically, it is an interdistillate capacitor on silicon. It has these are gold electrodes, and you can see in this SEM micrograph that the in between these gold electrodes you have nanotubes aligned in the direction of the electric field perpendicular to the electrodes, and that will maximize the capacitance. So so basically this entire area is covered by nanotube films, and that will change the capacitance and change the shape. Will give a shift in resonant frequency if this capacitor is part of a resonance circuit. And these kind of interdistillate capacitors are increasingly being used for environmental air quality monitoring, gases like ammonia, ozone, etc. Patient health monitoring, that's what I'm interested in. My research is funded by National Institutes of Health. Hazardous gas detection for industrial and occupational safety, and so on. But the most important property which makes this feasible is that the carbon nanotubes have the ability to be functionalized by polymerization or other methods to, to be very specific to a particular analyte. And this is very different from MOS sensors and electrochemical sensors. So this is an example of sensors that Elena, my collaborator, published. There are two graphs here. These are pure CNTs deposited on an interdistillate capacitor. And this is functionalized CNTs specifically to detect ammonia. you can see that when there is ammonia exposure, the resistance increases, and when the source of ammonia is removed, the resistance decreases. And this can cycle on and off depending on the exposure time. And you do the same experiment with a functionalized, very specific detector, functionalized ammonia. You can see that the sensitivity is almost doubled. Here, the sensitivity is about 2%. Here the sensitivity is 4%. Okay, so this is an example of how chemical functionalization can be used to make very sensitive detectors, which other methods are not so easy to make. And these are some of the advantages. I don't want to read through this, but I want to point out some very specific advantages. Very high sensitivity because of functionalization, low power consumption. You actually don't need any power. Why? These sensors can operate at room temperature. There is no heating of any kind. They have very low cross sensitivity also because of functionalization, and compact and low weight. Very fast response time. You can see it's tens of seconds. And one very big advantage is the sensor is reversible. When the source of the gas is removed, it comes back to equilibrium. It does not come back to the same stage because of chemical hysteresis and other properties. But there is a clear decrease in the resistance when the source of the gas is removed. So it is reversible, which means that the sensor can have long uninterrupted life. Typically, these sensors are projected to be used up to 6 months or a year. And finally, one very big advantage for engineers is that these sensors can be very easily integrated with electronics and wireless mobile devices like smartphones. Now, because I'm funded by NIH, I'm obligated to show the public health impact. Asthma, we are developing this for asthma. NIH is interested in fitting these kind of sensors on the wrist, on small children, for example, wearable sensors, so that their parents or the physicians can monitor what kind of gases they're exposed to. Why asthma? Asthma is the leading chronic disease in the world. 340 million suffer according to World Health Organization. Almost 60% of these are children. That's why this is very important. And high rates of mortality as well as morbidity. Many hospitals, I mean, it's well published in journals, the hospitalizations and so on. And it is the second most expensive disease in the world after cardiac disease. So what we are trying to do is to make a wearable sensor to provide continuous real-time monitoring of the pollutants the patient is exposed to within the breathing zone. And why this is important? Currently, we hear weather bulletins and we say ozone level is so and so, right? But as a patient, it does not help me because what I'm sensitive to is what is within my breathing zone, which is only 1 meter circumference around me. And these kind of sensors will provide that breathing zone exposure information. And this is an example of a sensor from UC Berkeley of flexible sensor array with the flexible electronics. And the idea is that we get the ozone concentration or particulate matter concentration. You can show the display on a smartphone. And not only that, we can have another detector to sample exhaled nitric oxide. When you breathe out, the nitric oxide in the exhaled breath is a biomarker for asthma. So you can detect that and you can show how your lungs are performing. So this can be a closed loop kind of sensing. You can also show qualitative alerts like air quality indexes and so on. And you can also be very specific on which chemicals is the patient exposed to and so on. So this comes to now. I'll talk about my particular contribution in this paper. This is an example of a paper where example of a resonator, circular disc resonator, where the entire top surface of the resonator is coated with an epoxy of single wall nanotubes, and they measure the shift in resonant frequency using a network analyzer connected to this coaxial connector. Okay, so you just look at this graph. The black line is this is an ammonia detector. The black line is before exposure to ammonia. And once the sensor is exposed to ammonia, because of the surface chemical reaction going on, the resonant frequency shifts to the left by only 4.7 megahertz. And when the source of ammonia is removed, the sensor reverts back to the original condition, the equilibrium condition. So it's completely reversible. But the problem is that 4.7 megahertz on a grounded plain patch resonator can be very easily detuned by, for example, if I place the resonator on this desk, I can move the frequency. So in practice, this is not useful. So what we did at Georgia Tech is instead of coating the complete antenna with carbon nanotubes, we created a short stub extension. And in the stub, you have a small gap. And across that gap, we put this thin film of carbon nanotubes, which are specific to ammonia. And we repeated the same experiment which the previous authors did. And what we found is that there is a 300 megahertz shift, not 4.7, but 300 megahertz shift. Now we can manage this shift along with amplitude discrimination and so on, and we can get a very robust way of detecting gases using this resonant frequency shift. And again, when the source of ammonia is removed, it comes back to normal. Again, as I said before, this it does not come back to exactly the same response because of the chemistry. It's not something which I can explain very well, but the chemistry is causing this. It's not the electronics. So we have published this paper along with Professor Manos Tenzeris and his research students in October 2011. We also were awarded a patent on this research. Now, this is the topic of my presentation. What I'm doing today is to actually report on a completely passive resonant sensor. So I imagine a dipole like this. The dipole is resonant at certain frequency. You can very easily design this on any kind of substrate. And I put a single film of some chemically sensitive material at the gap. So what I do is I put this on a pedestal and I have a horn antenna connected to a network analyzer. I measure the reflectivity of this sample using the received signal. So I'm basically measuring S11 of this horn antenna. And from there, I can look at the resonant frequency shift as a function of gas detection. You can see a small gas cylinder there, which is exposing the sensor. So first, we did some simulations. This is an example of the dipole. There are two vias going to the other side. There is no ground plane on this. It's a simple dipole. And I put a film in the gap on the other side, 10 micrometers thick single wall nanotube film with nanotubes very specific to ammonia. And this we did this on a Rogers substrate. In the model, we use a surface impedance for the CNT film. And we did extensive characterization of CNT and graphene films at microwave frequencies. And it's reported in these two papers. And we found that the resistance usually is a few hundred ohms, and the reactance changes by a small amount. So the surface impedance is primarily dominated by the resistance, which one would expect for a carbon material, correct? Carbon materials have high resistance. Their reactance is essentially because of parasitics and other things, but nanotubes themselves, they don't have too much of capacitance. Their kinetic inductance and capacitance are small values. So we found that the change in the resistance can have maximum impact on the sensor performance. So here I'm okay. Here I'm plotting some results at very small resistors. You don't have any resonance, but as you increase the resistance value around 800 ohms, you get a very good resonance. And this is an example of simulation versus measurement when there is no gas exposure. This is a simple experiment without any gas exposure. We get very good agreement with a resistance of 800 ohms. And this is the radiation pattern, about 3 dB gain. Radar cross-section clearly shows the expected pattern, the oscillatory behavior of a dipole with regard to scattering or radar cross-section. So we get a significant signal, as you can see from here. So a resonant scatterer also gives a resonant response in radar cross-section. And this is with and without gas exposure. The blue line is with no exposure. Once the gas exposure is there, well, there is a resonance shift to the left. The blue line is gas and the red line is no gas. So there is resonance shift to the left by about 25 megahertz. And this is my last slide. I already explained this measurement setup. So I extracted the resonant frequency from the dips in S11 and plotted the resonant frequency as a function of time for various gas exposure cycles. So for the first 5 minutes, there is no gas. For the next 10 minutes or so, there is gas, and then I remove the gas. So what happens is there is a downward shift of resonance because of the gas exposure. And when the gas is removed, it comes back to normal. So the sensor reverts itself. So this is the same phenomenon on carbon nanotubes, which many other researchers have observed this reversibility. It's very encouraging that our results are following the same pattern. So in conclusion, I have demonstrated a proof of concept for using resonant frequency as a marker in a completely passive scattering experiment. The future work includes actual realization of a small miniaturized radar system and doing some ambient gas sensor measurements in the field. Thank you very much.